Hi there, welcome back to section 4.4. We're in our last video of the last section of chapter 4, additional applications and exponential models. We're going to tackle use exponential and logarithmic derivatives in curve sketching here. We'll take one of the most classic models for using exponential functions, the logistic curve. So here's our function. 5 over 1 plus e to the negative x. So this function is often in some disciplines called an S-curve because the shape of the graph is kind of like an S. So it's got a lot of interesting characteristics for us to study graphically. So our job is to do the whole smorgasbord of stuff here. Increasing, decreasing, concave up, concave down, sketch a graph and show the high and low points, so in other words, relative maxes and relative mins, points of inflection, any asymptotes, intercepts, cusps, vertical tangents, all that exciting stuff. Okay, so first things first, intervals of increase and decrease make use of the first derivative. So we could take the derivative of our original logistic function, just going back to it real quick, of this thing using quotient rule, but maybe that's overkill. It's certainly not the end of the world, but we could rewrite this function as denominator to the -1 and then do power rule on this basically. So we would bring the -1 down, we'd have a new exponent of -2, and then we would need the derivative of the inside of this function. So the derivative of 1 plus e to the negative x. Well, okay, derivative of 1 is 0, so that's off. And then derivative of e to the something is usually just e to the something. But the one catch in this case is that we're dealing with not plain old x in the exponent. So the derivative of e to the stuff is e to the stuff again times the derivative of that exponent piece. So we actually have a second chain rule that triggers off of this. So now we have derivative of negative x, which is -1. So if we miss that, we would be missing a negative sign here, and that would certainly change some answers. Tidying up a little bit, putting the negative along with the -1, we get a positive, and now we're looking at this expression, 5e to the negative x times quantity 1 plus e to the negative x all to the -2. Okay, so here's the thing, that derivative function is always positive. Maybe I'll go back to it just for a moment. 5 is positive. E to the negative stuff, e is, this expression is always positive. This denominator piece, because it really is, it's to the negative power, this is all positive. So there's no way to get that derivative to be negative. So that must mean it's increasing everywhere. That also means it's got no relative extrema. If it's always increasing and defined for all real numbers, there's no other chances for us to run into critical points. So that actually cuts off a large chunk of our job. So now that increasing, decreasing is done, and we've established that there are no peaks and valleys here, then we can start working on the next chunk, which is concave up and concave down. Of course, that means we need the second derivative. Well, look at this guy. So here's our first derivative written inside there. This is f prime that we figured out just a minute ago. Taking the derivative of that requires product rule. There's stuff with variables, here's other stuff with variables, they're getting multiplied together, so there's pretty much no way around that. All right, so leave the first thing alone. So we think of 5e to the negative x as one quantity. The derivative of all this stuff is going to take a minute, so we'll spread it out and take our time. And then add on the other combination, derivative of the first piece, 5e to the negative x, and then times the other piece left alone. So here is derivative of, all right, so we've got a bunch of stuff to the -2 power. So we basically got power rule on the outside. So there's the -2 stuff to the -3 power, but actually all of this is part of that derivative. So here we run into that same issue again where we look at the inside function and its derivative. So the derivative of this piece is, like we encountered for the first derivative, derivative of 1 is 0, so that's out of there, plus the derivative of this, which looks initially like e to the negative x all over again. But then we'd have to tack on the derivative of negative x, which gives us this negative sign here. Okay, then we've got derivative of 5e to the negative x, and that's not so bad, although we do get a negative sign out of that. Same reason, e to the negative x has a derivative that's e to the negative x times -1. So that piece is going to change this from a plus to a minus. But now we've accomplished all the derivative stuff, so we've done all the calculus. Maybe there's some simplification that would be valuable here. So putting some stuff together, -2 times 5 times -1 gives us positive 10. We've got e to the, and this is a little bit weird, but e to the negative x times another e to the negative x. and let's see how many colors I can run through here. E to the negative x, e to the negative x. Those have the same base. The powers added together, negative x plus another negative x, make e to the negative 2x. And then we've got this big chunky term to the negative 3 just kind of hanging out there. Not a whole lot happens in this last term. 5e to the negative x times all this stuff to the negative 2. That's pretty much just sitting around. Here's the thing though. If our goal is to figure out concave up and concave down, getting this to as factored a form as possible would be really advantageous. So if we're working towards setting this equal to 0 and solving to figure out where concavity could change, then really we'd want to factor out as much as we could. And this is a little bit odd, but we can do this. This is valid. So if we pull out this chunk as a factor of everything, this might be easier to think about as a fraction as opposed to this multiple. But if we pull that out, that's essentially like dividing each of these two big old terms by this number. So if we divide this by itself, all that we're going to be left with is, well, we're pulling out even more. This piece is going away, but you also might notice that we can pull out some x stuff as well. Some e to the negative x's can get pulled out too, as well as a factor of 5. So if we think of all those things in magenta getting pulled out as factors from 1, 2 terms, this divided by itself is nothing. This divided by e to the negative x is almost nothing. And 10 divided by 5 is going to give us just 2. So if we pull out all this stuff, well, okay, so I guess I should illustrate this piece. If we pull out all of this stuff, we're going to be left with very little remaining from these two terms. So pull out a 5, the 5 is gone. Pull out e to the negative 2x, we've actually got a positive e to the x left over. And then if we pull out a factor of 1 plus e to the negative x to the negative 3, this whole monster thing, there's actually a positive power that remains from this one. So that's supposed to be a power of 1, not a prime. So this is actually only 2 powers left over, so if we pull out 3 of them, we're actually up to a positive value. So that algebra piece is got to be confusing if you don't do it yourself. So this usually won't come up, but it is actually manageable. So the advantage to that is basically figuring out where this could be 0. Technically, we should also check where it's undefined, but it turns out we're not going to find any of those values anyway. So all this stuff put together, we're supposed to figure out where these things could be 0. So we've got 5e to the negative 2x. That's really not going to work out. There's no way to get e to the something to be equal to 0 with real numbers. This is a similar scenario compounded by the fact that this is actually a fraction. This is 1 over 1 plus e to the negative x to the third. Having 0 in the denominator doesn't really help us out. So really, this is where all the action is. So finding where 1 minus e to the x would be 0 is actually where all the excitement comes from. So then we take that, we add e to the x to both sides, take natural log, and we get an input of 0. That's it. So if x was 0, then that expression would be 0 as well, the output. So we're supposed to test on either side of 0. So we're going to take the second derivative, f double prime, and check it any value on the left side of 0. It doesn't matter what. So but negative 1 is nice because it's a whole number at least, an integer. And then we get some approximate thing, but really the only thing we care about is that that's a positive number. So that must mean it's concave up on the left side. If we test something positive, so we test over at x equals 1, we get f double prime of 1, and that's something like, well, unsurprisingly, there's some symmetry here. We get something that's negative. But that's going to illustrate negative curvature. So actually we're answering two questions here. We can say that it's concave up everywhere on this left side, everywhere from negative infinity to 0, and concave down from 0 to infinity. And then we can also say that there must be a point of inflection right at 0 because it's changing concavity there. So there we are. All real numbers less than 0, we get concave up, concave down for numbers greater than 0, and an inflection point right at x equals 0. We're also asked to figure out the asymptote situation here. And as usual, we're sort of waving our hands at the vertical asymptote issue. The way we're looking for vertical asymptotes is by asking where would domain errors occur, and that's actually not a foolproof strategy, but it does accomplish the goal when we note that there's nothing that would make f of x undefined. If we try to make the denominator equal to 0, we come up with no real solutions. However, if we look at limits to infinity, then we're going to come up with some horizontal asymptotes. So remember, we're supposed to check both x going to positive infinity and x going to negative infinity to make this work. So here, if x goes to infinity, e to the negative x, this whole piece is going to go toward 0, which works out great for us, because that means that this limit is 5. So in the long run, so as x gets really, really big, this function is going to increase toward 5, or at least it's going to approach 5 in the long run, but it actually does increase toward that, this particular one. If we go to the left, on the other hand, maybe we need to do a little bit of manipulation, because what this looks like is e to the negative infinity. That's sort of positive infinity, and it's hard to say exactly what it is that's going on there, but well, it's not that hard. But so just to follow through with the algebraic stuff, to be diligent, if we multiply by something to make this piece go away, e to the x would do that. E to the negative x times e to the x is just positive 1. Now that makes the other pieces more complicated, 5 e to the x and 1 times e to the x, but that's actually a perfectly good situation to be in. As x goes to negative infinity, we know that these things go towards 0. So just like our usual strategies with infinity, whenever we run into things that look like infinity in parts of this fraction, we'll multiply by something to turn those infinite limits into 0 limits, because 0 is a perfectly good whole number to work with. So on top, in the limit, we get 5 times 0, and on the bottom we get 0 plus 1. So actually, if we move to the left, we get a different value from the one we got up above. So another horizontal asymptote is at y equals 0. So those are our two values. Horizontal intercepts. So we're trying to set this whole thing equal to 0, but if we multiply all this stuff over, we're really not going to get very far. So all this stuff multiplied by 0 is going to give us an equation that looks like 5 equals 0. Not so much. Vertical asymptotes are easier. We just plug in 0 for the x value. And this is going to be 1, so we're going to get 5 over 1 plus 1, 2.5. So we have a vertical axis, or a y-intercept, at 0, 2.5. The last thing we were asked to look for were cusps, or vertical tangents. So we're looking for where the derivative function, and we can dig this guy back up from a few slides ago, looking for where this thing is undefined. So really this would not work as long as the denominator was equal to 0. But the thing is, if you set e to the x equal to 0 or this piece equal to 0, you're not going to find any real solutions. So however hard we try to make this happen, we're not going to find any places where this derivative is undefined. So that should mean that the function doesn't have any cusps, that is, the derivative function is not continuous at that point, nor do we have any vertical tangents where the derivative would be infinite. So all that's left for us to do is get a picture of this. So this is a sketch that we could generate on our own, or by some sort of graphing utility, and then we can start identifying key features. Inflection point was right at 0. We found horizontal asymptotes at 5 and at 0. So we have, if you notice here, it's out to the left, it should be dropping toward that value and rising toward 5 on the right. And those are all the key features. That's it for section 4.4. We'll see you for chapter 5.